I know how much Pedro likes quotes. This first one, the difficult we do immediately, the impossible takes a little longer, was a favorite of my father. And I especially like this impossible takes a little longer. It had a heroic ring to it. That meant adventure in this word we're talking about tonight. But science has that character, as I mentioned already. They do things that seem impossible after a while, and I've explained why. And then Richard Feynman, science is not about what we know, it's about what we don't know. That emphasizes how rich it is. Whenever we do manage to understand some part of nature, it always shows us how much more we don't understand. Often on the way, we learn how to develop a new tool to look further, and then it tells us how much more. Nabokov, here's a nice quote. There's no science without fancy, there's imagination, guessing and all, and no art without facts. And we need to devise ways of teaching so students can guess and so on and not feel unhappy about it. And I've tried to do that. You can think of exams to do that. And then finally, one just recently learned, and I also put that here because it's appropriate to the Basque region, because the Jesuits were founded, as you know, by Loyola. We got a chance to visit the very site today. And Frank Wilczek, in his book, he's an outstanding theoretical physicist, several times mentions the Jesuit creed as the way he recommends to pursue theoretical physics. It's more blessed to ask forgiveness than to ask permission. Of course, what he means was, don't worry whether your idea is a little bit unconventional, unorthodox. Go ahead and do it anyway. If it doesn't work, you can always ask people to forgive you, but don't waste. Now, of course, in science is intrinsic. Who would you ask for permission anyway? So the point is to be bold and all. And then one final thing I want to show you that summarizes, in a way, the first part of my talk. This is something I saw in a science fair. And it connects, of course, with our biking adventures, especially in the cobblestone streets. But if you had the problem to construct a tricycle for your little child to ride on with square wheels, most people would think that's a little crazy, isn't it? But actually, of course, you realize it's not so hard to solve that problem. You just make this road to have distances along the curves that fit the side of the wheel. But the point is that most people are shocked when you think about this. But students in science fairs and so on, which I've had the pleasure of taking part in many, they get very excited by challenges like that, and they devise things of this sort. This was something students built themselves. I've ridden this very thing myself, and you can ride fine. You can roar right along. So now I want to go to the saga part. And again, I will give a quick menu, just glancing at the menu and then moving on. I want to talk about what I call the saga of space quantization. And I deliberately use that word. It sounds, uh-oh, what's that? It's not space colonization, which you might wonder, outer space. I think of talking on this topic and showing what follows from it. Because space is what architecture is about, the organization of space, and the discovery that in the atomic world, way down there, where we're talking about atoms the size of 1/10,000th the width of a human hair, that's a tiny world there, the space is organized in certain ways as well, that are defined by what we now call the laws of quantum mechanics. And I want to show you a quick scan, all the amazing things that really followed from one experiment back in 1921-22 that was designed to split molecular rays. Molecular rays. Okay, what does that mean? Well, the experiment was done, or the idea for it was done, led by Otto Stern. He's here. And you recognize this other fellow here, This fellow is famous for Gedanken experiments, that is, thought experiments. We're talking about intellectual things here, so Gedanken is the German word, the right word. Otto Stern got his PhD in 1912 as a physical chemist, and his thesis work would not sound terribly exciting to you. He studied solutions of CO2 in various solvents. In other words, generalized soda pop. That's really what his PhD thesis was. But his parents were so proud of their son, they offered to support him a year wherever he wanted to go to study further. And he'd heard of this bright young physicist, Einstein, and said, I want to work with Einstein. By what we would now call the old boys network, it was arranged, and so this physical chemist got to become Einstein's first postdoctoral fellow. They hit it off very well. Of course, he started working with Einstein in 1913. Very soon, World War I interrupted and all, but they wrote some theoretical papers together. And after the war, Stern got a position at Frankfurt University and began studies on what he called then molecular rays. What that meant was the invention a few years before of a high-speed vacuum pump meant that you could take a volume, well, it wouldn't work in the, maybe he was using the volume like this, say a wine bottle type volume, not very big, and evacuate it well enough so the remaining molecules would not interfere if you introduced a stream of molecules traveling through it. They wouldn't bump into any of the molecules that would ordinarily be there. And so that allowed you to consider possible experiments that could test what happened to the molecules, because the beams were the rays were so dilute that the molecules in them traveled independently. Later I'll mention work we did with this method. Now we call molecular beams instead of molecular rays. And here you seem to have test tubes, and as a test tube usually would, it's filled with lots of molecules, because ordinarily you have liquids in it. But if instead there were vacuum and you were having one of these beams or rays, there would only be about 2 molecules at most in this tube, this long, because their average spacing is very dilute. So they really move independently. If you have an external field, magnetic or electric, you can see whether the molecules respond to it independently. So you can make macroscopic measurements and detect what happens at the microscopic atomic level. Remember how tiny it is compared with our equipment. So Stern became interested in that, and I had the opportunity to meet Stern when I was starting my research as a young faculty member of Berkeley, and hear from him in person how he got the idea for this great experiment that had so many consequences that we'll quickly trace. He woke up one morning, it was too early to go to the lab. This is in Frankfurt. The Germans are very rigid when they will open the doors and all that. It was too cold to get out of bed. So he stayed in bed and thought of this experiment, because there had been a seminar the day before that raised interesting question. So that's moral number 1 of the story. You young people want to do science, sometimes you can do your best work in bed. You may have trouble persuading your research advisor that that's what you did. But what his idea was, I got in the wrong place to press the button, was based on what was called the Bohr model of hydrogen atom. Probably many of you encountered this in school. Bohr's model in 1913 was one that Stern found distasteful, because Bohr had suggested that the simplest atom, consisting of hydrogen nucleus, a proton, we call it, and 1 electron, you could imagine, he just postulated out of thin air, literally, that only certain orbits were allowed, that a certain radius and in which the electron traveled at a certain speed. Well, that seemed kind of doubtful, that you should just be brash and bold enough to say, yeah, I'm going to presume that. And of course, then there's two ways it can go, that way or that way. And the seminar had talked about the problem that if you had an atom that really is constructed like that, then in a magnetic field, here's your external field, because you have a current, a little current due to the charge on the electron going around, it generates a magnetic moment. It's perpendicular to the ring, points upward, labeled L here for angular momentum, a fancy word, but when you think about it, it's just angle and momentum. Momentum is mass and velocity, so it comes in. And then the other direction is going this way. So this one will interact differently with the magnetic field in one direction, especially if the magnetic field is stronger in one direction than the other. And this one would interact differently. So if this model were right,